Hi. So today I thought we're going to look at a little bit of ways of resetting transforms and working with already baked transforms and animations, which if you work, I mean, the ideal situation is that you don't get that, but in production, at least in my experience, you often get this kind of weird stuff going on, and you might get files from Maya, or you might get already baked transforms or such. So in this case, I just have a geo here, which I can also apply. You can get this very ugly kind of weird animation. But the thing with this is, if we just look at it, this is very similar to. The thing was, I did a project with something similar to this, but I can't use those project files, so I just did like a really fast kind of weird fluid thing. And the thing is here that we have this kind of thing which doesn't have a constant point count, so we get different amount of points, as you can see. So we can't use point number as such, which is always hard. And what it also has is this kind of tracking data applied to it. So we see you have to have rotation in all axes, and it has movement, and it's not very centered. So in this case, the fictional scenario is that the client wants to add ripples on top of this surface. And that's quite hard when we have this baked transform and we don't have point and we really don't have anything to go on. So the best option in these kind of situations, in my opinion, is to reset the transforms first, apply what you want to do, and then transfer it back to its place. And this can also be done. I mean, if let's say that we want to add extra sim to this or whatever, that would also be a very useful thing to do, to just reset it first so you have gravity up and stuff like that. So we're going to look at that, and I did this kind of transforming thing to make it a little bit harder, which I think is but this applies to, like, if you don't have deforming geo, it's a lot easier and you can apply the same kind of technique. So just going to get started here. As you can see here, we have this kind of weird droplet going through it as well, and that was just stuff like that can happen, so you can get these kind of weird things. So first of all, we need to handle that, so we only have this big chunk of stuff. So that's quite easy. I mean, we can just do a connectivity on primitives, and we can just measure it. And we can measure per piece, and we can measure the volume. And then we can do something as simple as just blast off everything that's too small. So we can say at volume is less than 0.1, and we just say primitives. So now we just have this. So that's one good step in the right direction. But now we need to find out the rotation. And here comes the tricky part. What you want in that kind of situation is some kind of primitives that stay stable, preferably like a surface or whatever that you can extract from. So in this case, I think the bottom is very much the best option here. And as you can see, it's kind of stable. It doesn't really change that much. And I think with just, although the point number changed, I think it still could be quite simple to maybe start by extracting the bottom. So let's do that. Let's start by doing a group where we look at the point normals. And we'll set this to -1 to look at those. And we bring it down to maybe 4 degrees. Something like that. 3 degrees maybe. Let's see. Doesn't really matter as much. And then we get something kind of stable. We get a little bit of changes. But those changes are so small, so we can probably handle it. So what we're going to do now is we're going to blast off this group and immerse it, so we only have this. And now we have something that's a bit more stable, I think. So what we can do now is that we could try to find the center point of these. And there's a lot of ways of doing this. I'm doing a kind of sloppy version or a fast version. So what I'm just going to do is just going to take all these positions and just going to average them out. And you can do that in Vex, but if you're lazy like me, you can also do it very simple with an attribute remote. So first off, I'm just going to say that I'm just going to do a new vector that is we call position2. And we're just going to say that that is equal to positions. So and we run it over primitives. So what we get now is we get like a position of the primitive. And that's the center point. So what we can do then is we can simply just promote this to detail. And I like to do this. There's probably better ways nowadays. Everything has become so much, there's so much soft for stuff, so I don't really remember. But let's just add position 2 and promote to detail. And if we do average there, we get the average position. So what we can see here now is that we have an average position of this, which is really good. So what we can do now is we can just simply do a loop where we look at all the primitives and we see which primitive is closest to the center. So that we're going to do in a wrangle, and this is the only little bit tricky part here. It's not very tricky, but if we run this over detail, we can first just say prims is the amount of prims. So we say m primitives in input 0. We can do a new vector that we just say like this, vector pos. I don't know why we do this. Actually, we could just use pos2, but I'm just going to do it like that. I like that. We forgot the equal there. So now we have the position. And then we want to find a primitive number. So we're just going to say, we're just going to do like an initialize an error kind of thing. So we call this prinumb is equal to -1. That means that we haven't found anything. And we're also going to have a distance attribute to calculate how far they are. So we're just going to say float distance is equal to something really high, like 10,000 or something, 100,000. And then we're just going to do a simple loop. So we're going to say for int I is equal to 0, I is less than prims, because prims is only the amount of primitives we have. And then we say I plus plus. So what this means is that we do a loop that starts with 0, I as 0. And as long as I is less than the amount of primitives we have, we continue the loop. And for each iteration, we add 1 to I. So eventually, I will become bigger than the amount of primitives. So what we do then is we just say like if, we're just gonna do one thing first. We're gonna calculate the distance. So we're gonna say, sorry, my bad. So first thing we're gonna do is we're gonna define the position of the primitive that we're iterating on. So let's do that first. So we say vector prim pos is equal to prim, which just reads a primitive attribute, 0, p, and I. So we just check each primitive. And then we're going to do a distance, calculate distance. We say prim dist is equal to distance. So we have pos, which is the center position, and we have prim pos, which is the individual position. And then we're just going to check if prim dist is less than dist, that is really high distance, which is really high from the start of. Then we can say that distance is the new distance. So we say prim distance. And prim num is equal to I. And that's, we need to end the if statement and we need to end the for loop. And then we can just say, we should probably have it here. That's pretty better. I was going to say, write this out. So I at prim, we just say is equal prim num. We get an error. Why do we get an error? What is wrong here? What the fuck? Let me see here. Oh, we forgot this. Sorry. And then we get done. Warning, because this is equal to prim dist. Oh, we call it prim dist and prim distance. Sorry. And distance. That's, oh, my bad. Distance. There we go. So then we can see here, and we go to detail, we can see prim. We have a prim, which is the center one. That's good. And if we then put on a blast, and what we can do here is that we can just reference this detail attribute. So we do this with this kind of, you know, backticks. So that's in my Swedish keyboard is like shift and the button beside the plus sign. So we just say detail, and that's because we don't want to evaluate this as a string. We rather want to evaluate this as a function. So we're just going to say, we're just going to look at this. So you can say point wrangle. We should get detail. Why don't I get little help thing here? Ah, there we go. Ah, one more like point. Attrib wrangle. Sorry, my bad. Trib. I should get some little help here. And then we're going to say we look at 0 here. And we get an error, so something wrong. Detail. Just going to rewrite this. Detail. I did one too many, sorry. There we go. So we look at attrib wrangle, and we look at prim, and we look at component 0 because it's not a vector. There we go. And we to delete non-selected, we get something that looks like this. It looks quite alright. So if we highlight this, we can see that we have extracted the center primitive here. And it works even though we have some things flickering here because it's pretty much the same. In the other project, I had to do some manual tweaks, so I had like a few frames that were off, and I just did a switch and deleted the correct primitive in order to get this kind of tracking data. So what you basically do here is you track a primitive kind of thing going on. So what we can do now is we can reset the transforms, which is simple. And if you don't have moving geometry, this is a lot easier. You just take a primitive and do it. So that makes it a lot easier. And I mean, this is very dependent on what you do. I mean, this is the hard part, finding this primitive and doing it in a good way. So, but when we've done that, we can simply just reset the transforms by saying translate the x-axis to negative center, the y-axis to negative center, and the z-axis to negative center. And what that says is that it just looks at the center of the geometry and it moves it by negative that. So if it's up 1, it moves it down 1, so it gets to 0. What happens then is we have this, it's zeroed out. And what we really want here is we want to output an attribute. We're just going to call that xform. So what's good about this is we get a detail attribute that says how much we moved it. So that way we can apply that to move the other geometry as well. And what we want to do now is now we still have this kind of rotation on this, as you can see. So now we want to reset the rotation. So how do we do that? Well, we do it in a point swap. I like to do it in a point swap. I know some people think that you should do this in Vex, but to me it's simpler and faster because it's easy to iterate, I think. So what we can see here is we have some point numbers. So we have 0, 1, 2, and 3. So what we can do is we can look at point 0, create a vector here to 2, create a vector to 1, and by taking the cross product of these two vectors, we get the third vector, and that would give us a transformation matrix, which is really convenient. So you need either a tri or a quad in order to do this. And preferably you want something that's aligned. You can do this on the side of the geometry as well, but then you would need to rotate it as well in order to reset the transform. But yeah, it's not that hard. So we're just gonna import the point attributes. So what we're gonna do first is we're gonna import. We're just gonna do a constant here. So we import primitive 0, Then we're just going to copy this, and we're going to import primitive 1. So just change it to 1 there. And then we're going to import primitive 2. Cool. So what we need to do now is we need to calculate the vector between 0 and 1 and 0 and 2. And that's also quite simple. So what we can do is we can just do like this, that we take a subtract. And what you want to do, if you want the position from 0 to 1, you extract 1 from 0. So that's a bit backwards, but if you look at it in a graph, you will see it's very logical. So if we do that, we take the point 1 and subtract 0. If we just plug that into normal, you will see that we get a vector that's that direction. So that vector is pointing in the direction from 1 to 0, 0 to 1. So if we then do the same thing, but we take 2 here instead, so we're just going to subtract from 2 instead. And if we look at that, we get the opposite direction. So that's good. And these move with this, so that kind of tells us about the transform. So what we can do now is we can normalize both of these values. It's always good to do when you do this kind of, most of the time it's good to do when you do this kind of thing. And what you can do then is we can do the cross product of these two. And what that gives us is the perpendicular plane of these two. So I can just show you what that would mean. So we're going to take the top one here. I'm going to do the cross product. Get some arrows because I have some bug. I need to just remove the configuration files, whatever it is. And if we look at the cross product, you will see now that it's pointing upwards. And since it's normalized, it's a little bit longer, but yeah. But we also want to do is we also want to normalize this cross product. It should be normalized. If you do the cross product of two vectors that are normalized, you should get a normalized result, but who knows. So what we can do now when we have all of these free, we can do a vector to matrix free. No, that's wrong. Vector to matrix free. Cool. And we take the top one, we take this one, and we take this one. And we're going to bind that as something called bind export. We're just going to call it rot for rotation. And we're going to say it's a 3x3 matrix. And where do we have those? Why am I blind? There we go. So if we want to as well now, we can remove this and we can do a quick visualize just to see that this works. So we take a marker, call it rot, label rot, attribute rot, and we do it as an axis. And yeah, here we go. And as you can see, this axis moves with our kind of thing, which is good. Yeah. So now we have that as well. And right now it's on points. So I'm just going to do attribute promote. Since it's exactly the same for all points, it doesn't really matter. So we can do point to detail, we say rot, and we can do first match. That's fine. So what we want to do now is we want to take our original geometry coming up here. And there we go. And what we want to do is we want to transfer everything to this one. So let's just go down here, make a new stream. It's not very nice, but we're going to do attribute transfer. And we're going to take this, and we're going to take this. And what we want here is on details only. And we're going to do the X form, and we're going to do the rotation. And what we can do then is we can do a transform by attribute in order to apply our X form. And what that gives us is it resets it on the ground plane, as you can see. And then we can just do a point swap. We can import detail attribute. Take that from 0. We say it's not a vector free, but it's a matrix free. And it's called rot. We can invert this vector. So we want to reverse the transform. And we can take a position. And we can multiply it by this vector. And we can store it out as position. It inverts it, but as you can see, we're now stable on the ground without any transforms. Really nice. So if we then reverse it, we have it looking like this. And then we have the simple task of just adding some kind of what's it called? Ripples on the surface. If you don't want to see this, just skip through this chapter because, I mean, this is quite basic, but I'm going to do it anyway because that was kind of what I set out to do here. So let's do it. First, let's just check what's the top position is. It's 0.68, good. Because what we just want on the top. So what we can do then is we put down a point fop. So let's start by creating a constant of the height. So 3 vectors, 0.68, cool. And let's just do the distance between the position and this. So let's put down a distance, take this value, put it into a fit range, and plug it into CD, reverse it, so get 1 and 0. And you can see here we get, okay, let's remove the color. You can see here we get this kind of color thing. So we probably want it less. Probably just want it like that kind of. And that's good. What we could do as well is we could actually, I think this is good. This is a good start. So cool. And what we also want is we also want to look at the normals. We only want, I don't think it's very necessary here because it's basically what's close here, but let's also look at the normals. So I'm going to do normal, and I'm just going to do a dot product of the normal. This is not strictly necessary, but it could be nice. And we're going to take a constant. So what we're going to do here is we're just going to see how big is the angle between our normal and something going straight up. So if we take this, I'll put in fit range as well. This would go from 0, 1 to +1. But preferably, yeah, you can see here we have this thing going on here. We have a little bit of stuff going on there as well, because I guess they're tweaking up a little bit. So we can just do something like this. And there we have something just looking at the normals. So we should get a little bit less on the sides here, which is good. Cool, so we have these two, and if we want to, we can multiply them in order to have the combination. You need to be close to the position, and you need to have the correct normals. So now we have something like this. So that's good. This is a good thing for our ripples. So what we can do then is we can do the distance thing here. Let me see, if we take the distance thing and we take the time, preferably. So it's going to take time here and do a little add. We're going to do a multiply constant here as well, so we can change the amount that time influence this. So we just add these two together and put them into a simple sinus function. And we get an error here, which is kind of not an error, but so what you can see now is put in a CD, we will have something like this. Not really what we want, but yeah. So what we can do now is we can, we have a multiply here for the time, but we also could do a multiply here for the frequency. So bringing this up will start to give us ripples. There we go, there's maybe something better, but now it's moving super fast. So we need to take down the time factor here. So we take it down to 0.4 maybe, and we look at it. So yeah, now it's moving, but it's moving inwards, I think. It's moving hardly at all. So let's bring it up to 0.1. It's moving outwards, but quite slow. And maybe we should skip, yeah, we should skip the position Y here, I think, because that influences too much. So let's just say 0, 0, 0 here, and let's just set the vector component of y to 0. There we go. So now we don't care about the y position, we just care about that. So now you get a more even outwards movement, as you can see. You can see what happens if we bring it up to 0.2. Yeah, that's cool. So we control the speed here, but we also get something around there. Why do we do that? That's weird, because the normal, yeah, That's of course because it's, yeah, we haven't really, yeah, that's why we need a more normal for. So what we can do now is we can do a multiply here as well. So let's multiply this again. And let's then multiply it by this factor. So there we go. Now we only have the ones normals pointing upwards, and we have more towards the middle and less towards the edge, which is cool. So what we can do now is we can do a simple displace along normals. And this will be the amount. The position will be the position. It's yeah, this is not very, this is not how you're supposed to do a network. At least we can do it like this maybe, but yeah, it looks like crap, but you get the idea. I don't really want to waste your time on doing this nice. So cool, this is way too much, so let's bring it down. Maybe that's too much as well. Something like that. So now if we remove the color, you see how it looks. That's too much still. Let's bring it down to 0.3 maybe. So here we have some ripples as well on the surface moving outwards. Cool. If you think they're too even, you can simply just do like this. Let's just, we can just add a noise here. So let's do an AA noise. Make it 3-dimensional. Plug in the position. And then just add that to the position. And that doesn't look very good. So better option probably is not to do like that, sorry. So let's instead do a 1D noise and add that to what goes into the sign. So let's do an add here before we multiply it. There we go. Now we get something a bit broken off. It doesn't move, it's very static, so let's change that. Let's do a vector to vector 4 here. Plug in time as well. And now we get something that's moving a bit outwards. We could, maybe it's too much. We could also look at this as CD just to make it a bit more, you can see here, you can see a little bit clearer what's happening. So I think this AA noise has to a high amplitude, so we just bring it down a little bit. We bring up the frequency a little, something like that maybe. So now we have, maybe we can bring it down even further, like bring it up 1. Or maybe what we need to do is actually take the time factor and make it a little bit more subtle. So we're going to multiply the time by constant, maybe 0.5. And now we have something that's a bit offsetted. We can see if we offset it a bit more, but it doesn't move that much. So that's cool. That's quite nice ripples. So let's move the color, just see how it looks. Maybe exaggerate a little bit just to see it a bit better. So do it like this. See, we have this. We added ripples to a deforming moving geometry, which sounds hard at the start, but as you can, oh, sorry, we need to have, it actually worked quite nicely. So cool. Now it's just a matter of reapplying the transforms, so the client are happy with that. So what I'm going to do is I'm going to attribute transfer the X-forms again. So let's take this and plug it down here, because it removes them when it applies them, the transform by attribute. So first off, we're just going to take this not this point swap, sorry, the old point swap here where we did the transform thing. Going to plug it down here. And what we're going to do is we're going to skip the invert. And that gives us now the rotation back. As you can see, it's not stable anymore. And then we can do a transform by attribute. We use the X form. And what we want to do is we want to invert the transformation. Don't have the X form here. Oh, sorry. This was... You only need X form. Actually, we're going to do rot anyway. So now, and then we can reverse the thing again. I guess it's something hooked up a little bit odd. So what we see now, we have the ripples. And if we compare it to what we came in with, it's the same thing, but without the ripples. So we have everything the same, but with ripples on the surface. And yeah, this is I mean, many situations are actually easier than this. This is a bit tricky situation because we did have deforming geometry and not a constant point count. And if you have stable geometry with constant point count, this gets a lot easier. But yeah, that's it. Hope you enjoyed this little thing. And I think it's a very handy trick for production. It's not a very fun thing to look at, but it's super handy when you get deformed geometry, moving geometry, things that are flying, moving. Reset them, do everything you want to do with them, and reapply the transforms. Thank you.